So do you share the web browser with the parallel computing with Python string?
Yeah, I see both.
Okay. So it's already 9 o'clock. Yes, and I can start slowly with this presentation. So the next 2 hours, I will cover topics related to parallel computing in Python. So we will see these topics here. What is parallel computing? Different parallelization mechanisms in Python. How to implement the basic parallel algorithms in Python, and how to use threads and workers in our HPC centers. So parallel computing sometimes is not straightforward, yes, because there are several packages available in Python, and that's why one usually, or in some cases, one needs to create an environment, right, as we have seen in the previous lectures, and then do some installations, right, for the software that we want to use. So if the software is available in your cluster, then you should go for it instead of installing it yourself with any of the methods that have been discussed, like Conda or PIP, right? Or any other, or even your self installation. So if the software is already there, use it. But in the present case, because we are using different clusters, right? And some of the versions of Python and the tool chains and the modules are not always present in all these clusters. That's why I prefer to use an environment, right? And then install the packages I wanted, just to make it compatible with the material that I have. So in these tabs, you can see the requirements, yes, that need to be done in the different clusters. But I will focus only on tetralit, yes, as it is a nice cluster, yes, and yes, and most of the so all these packages are available there. So these are the guidelines, and these are maybe updated. So in tetralit, right, we need to connect. So choose the way you prefer, SSH or thin link. I will be using thin link, as you can see here. Yes, and then I move to my project folder. In this case, is project Spring Courses NAISS user, my username, and then I create some folder there where I will be working today. So you need to follow these guidelines. You can follow them gradually as you go through the exercises and the material, right? So because some of these packages require some or several means to be installed properly, right? So in my case, because I already installed all these packages, it shouldn't take a long time to redo it. Yes. So I will load this environment that is available on Tetralit. And there are some recommendations here. So notice that I am connected to the login node on Tetralit. Yes, and these are not very heavy installations, right? So that's why I will load the modules directly on the login node. But a better solution would be to install to connect to a computing node with the interactive, let me see, the interactive session that was mentioned previously. Yes, and then you require some time, and here you write a nice project, right? In that way, you will be working directly on a computing node. But these are not very heavy, I would say, and that's why I will load the modules here directly. This module in particular takes some seconds to be loaded. Yes. This time was faster. And then we create an environment. Yes, and we choose a path, and I want the environment to be created in this particular folder, and that's why I will create it here. Yes, with this command. As it is here, right? So then execute this command, and it will create an environment there. So I already created the environment. That's why I can see it in my path, right? You see this here is my environment. And as I said, it takes some time to do these gradual installations. They are not very expensive computationally, but it takes some time to do that. And to activate the environment, we have seen previously the command, the source, and here we type em and beam activate. Yeah. So in this case, I have activated the environment, and I can start with the installations with PIP. In particular, we can install MPI for Pi by typing PIP install MPI for Pi. Yes. And it shouldn't take a long time, right? Because I already did it. Also, we need to install a number, which is a module that we will use later on. And here we install a connector with the Julia and Python, right? So you may say, well, this is a Python course. Why we need the Julia or any other program? And this is because I want to show you that Python can interact well with other languages. And these are only a few examples that I will show you, but Python can work with several languages, right? You can interact with C, C++, Fortran, Julia, right? And others. So I just want to give you a brief introduction on how you can interact with other languages, still being with the Python syntax. So for Julia, you need to do this extra steps. In particular, you load the Julia module. Yes. that you want to use. And then install this Julia call, and then inside Julia, right? You start the Julia session with the Julia command on the command line. You see here that I am inside the Julia REPL, the prompt, and then you go to the package installation with the bracket. You press the bracket, and you see here that I am in the package mode, and here I add this Python call, yes. And it will install the connector. So then finally I exit Julia, yes, and it should be there. So here is for the heat examples using the heat module, which can be relevant if you are using some deep learning, machine learning workflows, and you want to parallelize some parts of it. And this is for using the threading mechanism from OpenMP, which is a parallelization API, yes, that is available in Python in general, not only for Python. So as I said, you can do these installations gradually, as you did then during this lecture. So finally, you will be ready to do these exercises. So I will start with this brief lecture. So what is parallel programming? Is writing code, yes, that execute tasks on different computing units, which are called cores. And the key word here is simultaneously. So you have seen this word during the lecture, right? A course. And here is a definition. So some decades ago, when the computing, yes, the computing science start and there's a, well, it started, yes. So the CPUs, the central processing units, were shipped only with a single core, right? And the programs were executed in that sense serially, yes. So which means that if you have several tasks to be executed, then one has to manage to execute one by one in a sequential mode. And this is basically what we do in a Python script if we don't introduce any parallelization mechanism, yes, either explicitly by coding or in a Python script or by using an external library. So, but nowadays, the computer architecture are more complex than that, right? And here is a simplified structure of current architecture, but they can be very complex nowadays, right? You can see here the basic shared memory architecture and the distributed memory. In shared memory, the main feature is that the different cores, right, can share some address, memory address space, yes. And the advantage of doing this is that the bandwidth is very high, right? Which means that if one of these cores wants some data from the memory, it can get it in a very fast manner, right? And also, if one of these cores wants to update the data, yes, it can transfer back and forth the data, and then all the data residing in this address space can be visible or accessed by the other cores. So notice that I am depicting only two cores that share memory, but in our clusters, for instance, Kebnekaise Dardel, there are some nodes where about 128 cores, yes, can share the same memory address space. Yeah. So you can see that if you have some manner to parallelize your code, yes, that uses shared memory, you can take advantage of this high bandwidth. But in this case, right, in the shared memory, all these cores are sitting in a single node, right? And if we have a program, let's say, that can scale beyond the number of cores in a single node, right? So then we cannot use shared memory anymore. So we need to go for something larger than that. And for this case, we have the distributed memory where we have a cores, right, that can in principle share some memory or local memory. But when they want to update the data or fetch and put data on the other cores, so they need to use some message transfer mechanism. Yes. Like for instance, imagine that you want to update your colleague, yes, with some news. So then you can send a letter or an email and receive back some message. So you can imagine here that the bandwidth for transferring data is lower in this case, right? So if you have a code that only requires up to some number of cores, let's say 120, 128, the maximum in our clusters, then shared memory is an option. But if you have a code that can scale beyond this number of cores, if it is computing intensive, then this is a recommended way to program your code. So here is a standard node. Kebnekaise is a bit old. It's in this case, but the architecture is similar to what we have currently. Yes. I mean, the general features. For instance, here you can see that in a single node, that it covers all these pictures here, we have up to 28 cores. You see here, there are 14 and 14. And here, very close to the CPUs, we have these little boxes that are some local memory, yes, that are available to the cores. And you can see here that we go from one L1, L1I, L1D, L12, L3, and here you arrive to the memory available to all these cores, yes? And this part here is called the socket, right? So when you go, yes, up in this memory hierarchy, yes, the bandwidth decreases. So in this case, if the core tries to access the memory allocated here, this is a very high bandwidth, yes, but it decreases here until you get to the RAM memory available for all the cores. But even in this case, the bandwidth is very high. But now, when you connect to or you transfer data to other nodes, so the memory bandwidth is even lower, right? So here there are some numbers. In the case of the L1 cache memory, it's called L1 cache in this case here. So the bandwidth is in the order of terabytes per second, while if you want to transfer data between nodes, so it is in the order of gigabytes per second. Right? So the problem is that you cannot put all the data that you need here very close to the core because this is expensive and yes, there is no that technology to do that. So you can see that there are several types of memory available. Some of them are very close to the cores, as I mentioned. Some of them are shared among all these cores, and they are is sitting in a single node. Yes, and this gives rise to the concept of non-uniform memory access, right? Because there is a hierarchy of memory levels available. So besides the standard CPUs, we have also the graphic processing units, GPUs, also available in our cluster. And after this lecture, my colleague Brigitte will talk about the GPUs in more detail. So why a parallel programming is needed? So there is no pre-launch, which means that if you write your Python code, yes, without adding any explicit parallelization layer, either implicitly, yes, using some external libraries or external software, yes, in your Python code, or explicitly by writing the parallel code yourself. So you will end up using a single core that I mentioned above. Right? And you can see here that in our clusters, there is a hierarchy, right, of computing resources going from the single cores that I mentioned, where the cores share some memory. Yes, we have seen that there could be sockets in the nodes. Yes, and all these nodes are connected to some interconnect. Yes, and because of that, they can share data through some message passing mechanism. In order to take advantage of all this computing power and memory resources, so you will need to to use some parallel layer in your Python script. Other than that, you will end up using a single core. Even if in your batch script, you allocate many cores and many nodes, right? So writing the parallel code is one thing, yes, that we need to take care of. And another thing is using these resources, right? So imagine the extreme case when you write a Python code, you forget some libraries or some special option in your Python script, and you allocate uh, several nodes, yes, and all the cores in these nodes, and then you submit your script. But at the end of the day, your script is using one single core. Okay? So these are several things that we need to consider when we are parallelizing our code. And here you can see uh, how it looks like in a pictorial manner. So when one allocates several machines, but at the end of the day, one is using just a tiny bit of the allocated resources. So fortunately, in our centers, we have several tools that we can use to monitor the resources. And especially I like this one that is present in some centers like the C3SC and also HPC2N. It's called job usage, where you have a graphical interface that shows you how the resources are used. So if you're interested in that, and I really hope that it is installed on the new machine arrays. So here you can see monitoring the usage of resources, and here is how to use that. And there you can see, for instance, in this simulation, where you allocated some cores and also some GPUs. You can see how the CPU part is used, how the GPU part is being used, and also the memory and some information about the file system here. And here is the condensed information for the GPUs. So it's a nice way to monitor the resources. As I mentioned previously, imagine that you allocate more than what you need, or even another thing that could happen is that you allocate less than what your script needs. Uh, so imagine that you allocate only 2 cores, but in your script you specify that you need 20. So then immediately in this plot you will see a red line saying that the resources are oversubscribed. So, but in other centers, this tool is not available. So they have other tools. And a common tool that you could use is the top command, especially if you are using an interactive session. Other than that, it's very difficult to say how the resources are being used. You can get some statistics from Slurm, but a visual picture illustrate that better. So I will show you now how to parallelize uh, a Python script. Which is very simple. Here is the idea. We have a simple for loop, language is agnostic. So you can use this for loop in any language, right? So here I am saying that the counter I for the iterator I starts from 1 and ends at 10 at 4, and then I will wait for 1 second and I close the loop. So this is how it looks. So we start one iteration that waits for 1 second, the next 1 second, and so on. So in total, it will take 4 seconds, right? So the waiting function or the waiting instruction in this case is just to simulate some work that you will do. Yes, to simplify the coding, right? But in general, you can put more complex functions here. So in total, it will take 4 seconds. Yes, and as you can see here, it says serial code because if I not telling Python that this will run in parallel mode, it will use a single core or CPU. I call it in this case. And the idea of parallelizing the code is that we could distribute this task among different cores or CPUs. This should be called a core here. Yes. So that, for instance, if I have 4 iterations, then each iteration will be executed by a single core. So you can see here that in this case, the total time will be 1 second or 1/4 of the initial serial time. So this is the basic idea, yes. And here is an example of this code in Python. And to simulate the waiting function, I will use the sleep function that is available in Python. In other languages, they should have another function, yes. And it is called n times. And to parallelize this code, I will use the multiprocessing module. Multiprocessing is very useful when you are just starting parallelizing code in Python. It's very convenient, right? If you want to start with your code, then this is a good option to start with. And one of the reasons to use that at the beginning is that this module is part of the base library in Python, so you don't need to make any installation. If you see in the requirements, I didn't mention that we need to do a pip install multiprocessing because it should be available in your Python library. So here is what I will do. So I will start importing some libraries, especially to monitor the performance of the script. I will use the performance counters, and then I will load the sleep function and also import multiprocessing. So here is a basic Python example or how I will code the for loop that I listed above. So I define a function called sleep serial, yes, and it takes as an argument the number of iterations. Then I write a for loop, and then the sleep function for 1 second only. Yeah. And here is the parallelized version using multiprocessing. In this case, I call the function sleep threaded, and then with some number of iterations, some number of processes, and the process index to identify which process will solve the part of the iteration in the loop. So here I create a workload for each process where the workload is the number of iterations divided by the number of processes. So in this case, you can see it's very simple because the number of processes is equal to the number of iterations. So this will be only one iteration. But if you have more iterations here, then each process will execute some number of iterations accordingly. So I define here the beginning and the ending of the interval that will be solved by each worker. And here finally I run the iterations according to the beginning and ending for each process. So then I call the start time and end time using the performance counters for the sleep function. So here I print out the time that it takes using a single core. And here is the parallel version, right? So here we need to define the list of processes. So then we execute the processes. So with this multiprocessing process function that is available in the multiprocessing module, and it requires these arguments, the name of the function, and the arguments of the function here. So then we append the processes, and then we start, yes, the processes. And after that, we need to collect the results, yes, from the processes. And finally, we report the time. So how to run this function? We can do that in several manners. As we saw before, we can write a batch script, yes. But because this is a very short example, I will use srun. As follows. So I will specify 4 cores, 1 task, because it is a single script. And this is the function, yes, that I will be executing, sleep.py. So, but if the script is very time consuming, so then you can write a batch script. This is very short. That's why I will only use srun with these options here. Yes, yes.
Uh, Hello.
Yes.
I want to ask something regarding serial and parallelization.
Mhm.
So, based on the picture you showed before, it seems like serial use literal resources, but it takes time. And for parallelization, like you use more CPU, but in short time. So when do you have to trade off between serial and parallelization if you want to save resources, or when you want, I mean, at what time do you have to choose which one to use?
Yes. So it depends on several factors, right? It depends on your workflow, and sometimes it also depends on how much time you want to invest in parallelization, right? So, for instance, uh, when I talk with some users, right, sometimes they say that a Python script takes only a few hours, right? But imagine if they could run it in some minutes, right? So, but as I mentioned before, you are realizing about this. This is not straightforward, and one will need to learn gradually, yes, and how to parallelize the code. So when it is convenient, so it depends on your needs. Some people are uh, are okay with running a Python script in serial mode in some hours, as I mentioned. But imagine that you have not only one script running for 1 hour, but you have 100 scripts that take 1 hour, right? And you are able to parallelize the code. That will be yes a good choice, right? To go for a parallelization scheme. So it depends on the number of simulations that you want to do and also how long time they take. So imagine that you have a simulation that takes uh, 20 hours, but you only need that simulation once in a while, maybe one per year or something like that, right? But if you are using that particular simulation every day, yes, and running for 20 hours, that it's too much. So it depends strongly on the workflow that you are following, right? And yes, one needs to learn gradually.
Thank you.
Yes, I will go through some things that you need to consider when you parallelize the code, right? So, and here you can see the output, yes, of the simple code that I run. You can see that in serial time, it took 4 seconds, and in parallel mode, it took 1.01 second. Yeah? So the perfect scaling will be, which will be a 1/4, one, yes, is uh, statistically not achieved, right? So you will see some overhead, which is caused by several factors. One of them is the parallelization you follow. Another thing is what other processes are running on the CPUs and the transfer of data, many things that you need to consider, right? But yes, as a roof or of an upper bound of this parallelization scaling value, you will see 1/4 in this case. Yeah. Notice that it is not always straightforward to parallelize the codes, and there could be workflows that cannot be parallelized. Yeah? That's the reality. But you can find maybe a different algorithm, yes, that can perform the same or similar calculations, but in that new algorithm, you can solve the problem in a parallel mode. And here is an example that of an algorithm that cannot be parallelized in a straightforward manner. So you can see here a similar for loop as I run the previous step. So it's a for loop iteration from a range 1 to n, right? and I initialize the first value, A0. And then this is very common in research software, right? Where one tries to get the iteration I based on the value of the iteration I minus 1. So if you run this with Python, yes, it will give you the correct result. But notice that I am using a single core in this case. Yeah, single core. So if I apply a similar algorithm as I used before, just by dividing the workload and doing this processing, then most likely I will get the wrong result. So let's say we have these elements from 0 to 5, and we have two processes. So if I apply the previous algorithm, the first process will take the elements 0, 1, and 2, and the next one, the second process, will take the elements 3, 4, and 5. Yes. So notice, because the loop iteration I depends on the previous iteration I minus 1, so the process 2 will have conflicts computing A3. Yes, because it depends on A2, which maybe is updated at the time that it wants the value. Yes, it's updated by the process 1. Yeah. And you can see that this is a conflict. This type of loops is very common, and we have other loops that have a similar situation, right? And some of these loops cannot be straightforwardly parallelized for this reason. But for this loop in particular, we can transform that and use this instead, which does the same thing here. It does the same thing, but notice that here the iteration I only depends on I, right? So in that case, I can go with my previous algorithm that I wrote before, where I divided the workload and so on, and then this will run in parallel mode. And this is a situation that you need to consider in your code, right? Some algorithms require some refactoring, right? Or creating a different algorithm. So you need to change your mindset when going from serial mode to parallel mode. So I have a couple of exercises here that you can try now. So you can take this 10 minutes and even 10 after the break to run them, right? And see, have an experience on how to parallelize Python codes. So you can start with the exercises. Let me see the schedule. We have until 10 for the exercise. Then we will take a break of 15 minutes, and then we can return. Yes. I will continue with the next part of the course, of this lecture. And here I will explore a more elaborated example. And this will illustrate several concepts, yes, that you will need to consider if you want to parallelize your code. So parallelizing code is not something that you must do, let's say, in a cluster, but it can improve the efficiency of your simulations, especially, as I said, if you require many simulations, right? Or some simulations that take a long time. So parallelization is also not only available in Python, but also in other languages. And the concepts are very similar, yes, and the problems that you need to face are similar in all these languages, like the data dependency in the for loop that I mentioned above. So here is a more elaborated example. It's for a 2D integration, right? So we know analytically, yes, the solution of this problem. And this is very useful because we already know that if we code this problem and if we parallelize that using different approaches, we must get something very, very, very close to zero, right? We did the precision of the machine. Otherwise, yes, you can invest many hours in the code, but if the solution is not correct, it's not useful, right? Even if you achieve a very high speed. So how to parallelize that? We can create a grid in the directions X and Y. And this means that we can divide the integration range into n bins, yes, discretized steps. So this is a way to parallelize that without any optimization. And you see here that they specify the grid size, the number of points in the X and Y axis in both of them. So then I start the main function and start the counter for the timing, yes. Then I use a variable for collecting the summation, yes. Here, this will give me the size of the interval of the bin size, yeah. This is a cumulative variable, yes, only inside the loops. And here I start the loop in the X direction. And here is how to get the value of X, yes, using the bin size and also the part of the X-axis where you are sitting at this iteration. 0.5 is just to reflect that we are at the middle of the bin, right? And we do the same for the Y direction and collect the result here. And finally, we get the integral by multiplying the summation and with the square the size of the bin because this is two-dimensional problem. And finally, we report the time. So we can run the code. If you're in our own machine, for instance, we can execute basically Python and the name of the script. And this will give us some number. And even if you are using an interactive session in some clusters like Tetralit, as I mentioned before, with the interactive command, then you can execute that directly. But if you're on the login node, then you will need to use either a batch script or the line, as I mentioned before, with srun. So I will try that. I already have this code here in my folder, integration, the 2D serial initial. It's basically here. So you can copy the code with this button and paste it in your folder. And I did before. So this is the code, right? I can execute that with srun. So because it's a serial code, I will use one task for the script and only one core per task. And then I can execute the script. So this time, this reported time will change. So when you are doing some benchmarking, you will need to run that several times to get some statistics, right? So, okay, so while we wait for this result, that we can continue here. So this was what our initial function. Yes, see the structure here. So, but it is better. You see here, this is the time, 28 seconds. It's about the same time, but it differs by some fluctuations. So one thing that it's highly recommended if you are trying to parallelize the code is to divide the pieces of code, yes, related to the same feature into functions, right? What it means is that if you remember above, I have a plain code, yes, without any structure here. But because I know that this part, for instance, is related to the integration to D, there could be other features, right? Like, I don't know, computing the statistics or other features. But this is the one I am interested in, and I want to parallelize. So then I can enclose that in a block of code, as I did here. So I know now that this part is related to the integration to the. So this is highly recommended, not only for parallelizing your code, but when you're writing the code, because it is easier to debug later on if you find some errors, right? And if you have also developers in your group, it's highly recommended to do this. So I know now that this part is related to the 2D integration, and that's why I wrote it into a function here. And notice here that the timing is more straightforward because I can enclose just the function into the timing performance counters, right? And report the time. So it's very simple in this case, the code that I wrote, yes, but it could be more complex than that. So in this case, I only have one feature reflected in this function, right? And I discovered that this part is the bottleneck of my simulation, and that's why I can start thinking about parallelizing this part. Notice that in general, not everything that you write in your code is the expensive part, right? There are some parts that could be the bottleneck, and there is where you could focus your attention. So in this case, it's just this serial part. And notice that before going into the parallelization stuff and learning other packages you don't know at a time, right? So Python already offers you some options to optimize your scripts. Yes. And Numba is one of them. So it works by using decorators or functions. Yes. As in this case, the ngit function. So here I have basically the same function as before, right? But I also call in this case Numba, and that's why I install Numba with PIP in my environment. And here, basically, I only need to put this or a close the function that I am interested in into the decorator and ngit. Yes, and this can help me to optimize the code. I can run this. I already have that in my directory. Let me see. Number. See what we get. So previously when I run this code, I got 1.9 seconds, and you remember that without this decorator, it was about 27 seconds, right? So just by closing that. And that's another thing, another important point of why we need to close the code we are interested in functions, right? Because in that case, I can optimize that with other mechanisms in Python, like Numba. But if we have a plain code, as I wrote at the beginning, then using Numba for the entire script is not valuable, because we could have things related to writing a file, reading a file, doing some other stuff, and simply Numba with this complex task cannot give you an optimized code. But if we know the bottlenecks and we can write that in a more simplified manner, Numba can be your friend. You can see here that the time decreases just by enclosing the function in this decorator ngit. And you don't need to make any parallelization, as you can see here, right? But also notice that this is a very simple function. You can have even more complex stuff, but Numba we can help you, yes, potentially. So this is one serial optimization that you can make. Another thing that you can do, if you already know other languages like Fortran, C++, right? So then you can write the bottleneck in those languages because they are faster than Python. Yes. So for instance, in the case of Fortran, if you know already Fortran, so you will write something like this for the function, yes, that I know that is the bottleneck of my simulation. And then we can generate a module for Python, yes, that uses this function here. So for UPPMAX, we need to do these extra steps, but for the other clusters, we can simply write the function here, as you can see here. Let me see, Fortran, it's here. This is the function, but written in Fortran. Something similar can be done with C and C++. And in C, there are even better integrations with Python, right? So in order to generate the module for what is called the API for Python, we can run this script here. So you can see here that basically, if you know this stuff, you know that Python is compiling the Fortran code, right? So, and it generates the so-called API here, which will be used by Python. No, CPython. It's using CPython in the backend. Yeah? So it should be now listed here. You see the API here, and this is what Python will call. How to call this API from Python? So you write this Python script, yes, and then you import the function with this function name here, and extract the function that is there, which is called integration2D. And you will see immediately and speed up. I can try that. Yes, and we can wait. Well, you will see the result when it comes, but you can see here that the time decreases considerably because this language, compiled languages like C, Fortran, they are very performant or more performance than Python. But you know one drawback of this approach, and you have seen that when I executed the Fortran to Py function, is that it will try to compile the code. Yes? So, but if you are still developing the code, the Fortran code or the Fortran part, then it sometimes is tedious to recompile the code. And for that reason, one can use instead another language, right? That is more performant than Python, and that also don't need to be recompiled. The choice here it was Julia. You can use another language as well. And most likely, Python will offer you some options. So you can see here the script for Julia, yes, for the same problem, integration2D, and this is how we will run, how we will code that. Copy this, and then you can paste this in your folder. As I did here. Then we need to call the Julia script, and there are several versions that you can use. In particular, if you're using the ones on Tetralib, which is 1.9.4 and 1.10.4, then this is the script that is used. Notice here that I am calling the Julia script. We are using the connector that we installed before in the requirements. Yes. And here I am calling the Julia function and reporting the time. So I also have this code here in my folder. As you can see here. And then we just run the code. Yeah, and you can see here that the time is similar to the one we get with Fortran. Yes, because these are very efficient languages for computation. So, and the advantage of Julia in this case is that you don't need to recompile the code. You see here that I didn't compile anything. So if I change this script, so the changes will be reflected immediately when I call the Python code here. Yeah. So here I summarized the packages and modules that are available in Python for doing the parallelization schemes. So we mentioned at the beginning that we have shared memory and also distributed memory. And here are the packages for modules in Python. Here we have the threads, implicit threading, OpenMP, and PyOMP. Distributed memory, we have the distributed package, MPI, and HIT and DASK. And there are many more, right? These are only the ones that we have seen up to now in the course. But Python has a very broad ecosystem. So starting from the shared memory, we have the threads parallelization scheme, and Python provides you with a module called threading, which is built into Python. So traditionally, you won't achieve any speed up with this package because Python serialize the code, traditionally. But for Python versions greater than the 3.14, they have enabled the threading parallelization. So you have a Python version greater than this one, you will see the usage of the threading model. But I would say this is still experimental. So even if you have in some centers this Python version installed, it could be that the threading module don't give you any performance gain, right? So because you need to compile Python in some particular manner. So what it's coming. This part is coming. The threading mechanism in Python. So how you will use the threads? Yes, and notice the nomenclature. Yes. So each module will give you a different nomenclature for the instances, of the software that are solving the problem. Yes. When you talk about the course nodes, it is related to the hardware, right? But when you are talking from the software side, you will hear and read about different nomenclature. For instance, if you're talking about the shared memory, the instances that are solving the problem are called threads in general. And when you talk about distributed memory, you will hear about processes, ranks, workers, right? Depending on the software that you're using. So in the threading package, you will see something like this. Threading is built in Python, and here is what I did to parallelize the function, similar to what we have seen before, dividing the workload by the number of threads and defining the lower and upper bound for the integration. And this is a new thing that I introduced here. I allocated a shared array. You remember the shared memory? This is similar because in this case, all the threads will see this array, right? They could write and read on this array. Otherwise, each thread can perform any calculation, but they don't have a way to store the data that they get. In particular, to store this value here for the partial summation. So and finally, we create a list of the threads and execute the threads. and report the times. So you see that the time it doesn't decrease for this Python module, but as I mentioned, this threading mechanism is coming. So another way to use threads, yes, is by using a implicit threading in existing libraries. For instance, the linear algebra libraries like OpenBLAS, LabPack, MKL, and others. Yes. So if you are doing some matrix or vector operation in packages like NumPy, then it is using NumPy is using some of these libraries, and you don't need to do the parallelization yourself, right? Someone did it for you, and you are just using that particular function or library, and then using the parallelized program, right? So you also need to know how to activate the parallelization layer from the library. Some of them have an OpenMP parallelization already, and you can activate that by using the so-called environment variables. So, for instance, let's say we have this code here where we define a random matrix of 3000 by 3000, and we are using NumPy, right? So with NumPy, we do the dot operation for this matrix with itself, and then we report the time, right? So this is the variable that we can use, yes, to activate the threads. So in this case, I will use just one thread, yes, and then execute the code. And in this case, you see, it gives me 1.14 seconds. And if I use two threads, I will have something like 0.6 seconds, about half of the time, right? So notice I didn't parallelize anything. I only need to know how to activate the parallelization layer that is already in the library. In particular, with NumPy show config, you can see what libraries are being used with OpenBLAS, LabPack, and MKL, and some of them can differ in the way that is used, yes, to activate the threads. Yes, in this case, it was OpenMP, yes, that was used for the parallelization. So, and you see here the difference in the performance, right? So notice that if I go for something like two threads, yes, then I need to change this number of cores per task. Yeah. Otherwise, as I mentioned above, I will be oversubscribing the resources, which is not critical in this case because there are only two threads, and the script is very short. So you see that it depends on the statistics, right? Here I'm getting something similar, but in general, you will see about half of the time. So OpenMP, the parallelization mechanism that I mentioned, can also be implemented in languages like C and Fortran. There is an example, which is a bit more elaborated than the one that I described above. And in OpenMP, you can use this environment variable to set the number of threads. Yeah, and you can see that the improvement is about 1/4 of the time that I got before. So, but here there is a more advanced topic, and it's also a module that is being developed, is PyOMP, where you can write a Python, OpenMP code, but directly in Python. So one drawback of the Fortran or C code is that it needs to be recompiled, as I mentioned previously. But with this library, you can write OpenMP code, yes, directly into your Python script, and you can use the shared memory advantages for this. So you can see here how it performs. Notice here that the time is 120 seconds. Yeah, and here is 36 seconds. Is much longer than we saw before. And why is it? Notice here that I am using 10 times the grid size than previously, because this is what was very fast, right? And using a parallelization, I couldn't see the performance gain because it was very, very fast. So I need to increase even the simulation size. So that was for everything for the shared memory. Python also have modules for distributed memory. And we saw at the beginning one of them, which is a multiprocessing. Yes. And this is an example for the multiprocessing using the integration 2D. So we define again number of processes. And here we use an array that is visible by all the processes, right? And where all processes can read and write. So this will allow us to collect the partial results from each process. And we did it previously in our example. So the idea is the same as before: define the beginning and ending of the array, collect the partial summations, start the processes with multiprocessing, collect the results, and then perform the summation over the partial integral values. Yeah. You can see here how you can run the script. Notice that I am using 4 processes, and because of that, I need to use 4 cores. Yes. So MPI is more advanced. If you know already how to write MPI code in C, in Fortran, in other language, so then you can do this parallelization in Python as well. And that's why we install MPI for Py at the beginning as a requirement. So here you define the runs, yes, that are available for the computation. And then you do the parallelization of the function. And the idea is similar to what we have done up to now, right? And to collect the final result, API for Py has a reduce operation, right? So in this case, we run the script with npm run mp and the number of workers or the number of runs in this case, and the name of the script. So here is how I run that on a Tetralib. And this is there are other templates for the other machine. So notice here I am loading the environment, specify 4 tasks. Yeah. Activate the environment in the path where you have it. And then I am using the npm run mp4, yes, Python and the name of the script. So this is the way that I found that worked on Tetralib. So I couldn't run that with the srun, with the strict that I showed you before. There are some conflicts in the manner that npm run is used in Tetralib, and that's why it's more convenient to write a batch script. So heat is also more advanced if you are performing some parallelization for a deep learning, machine learning workflow, and which uses a PyTorch. Then heat is an efficient manner to parallelize code. We saw previously Dask, yes, which is another module in Python. So in heat, you define objects, right? And heat gives you a tensor, a torch, tensor objects, and also some local, global objects, and also some global objects, and also some local objects, right? So then, and these local objects can help you to parallelize your workflow. You can see here, if you run this script, and this is a way to execute the code on Tetralib, yeah, and using only two processes. Yes, we need to allocate the GPUs because this package uses some CUDA dependencies. And here you can see how to execute the code. So there are some examples where you can see the usage of this library, and you can also learn more about that. This is an alternative to modules like Dask. Here there is for distribution of matrix operations. Yeah. One of them is using CPUs and another the GPUs. And also this is a bit more elaborated using the gradients, right? Distributing gradients in a workflow. So monitoring resources. So I mentioned several times that it's highly recommended to use an optimal resources in our clusters, not oversubscribing, not undersubscribing the resources. And we have tools, I mentioned them at the beginning. And this is the one that we have at HPC2N called the job usage, yeah, where you can monitor in a graphical manner how your resources, your allocated resources are used. So I provide you with some examples, exercises here, so you can try that. This is similar to what we have run up to now with the 2D multiprocessing. And here you can run that with several, with different number of cores and monitor the performance, especially if you have in your center graphical software like your usage, or otherwise you can use top if you can connect to SSH to the computing nodes. And this is also more advanced, right? You can try that. But also it's more realistic because several researchers are using data frames or databases, and they want to parallelize the operations, right, on the database, and to reduce the computation time. And this is a nice example to show you how to parallelize the operations on individual columns of a data frame using the Python tools that we learned today. So you can try that, and yes, and let me know later on if you have questions about this. So let me see how we are in time with the time. So we have a break now. So you can leave the exercise for later on during the course, right? And if you have questions, just let me know. Yes. So but now we have a break, and we will continue at 11:15 for the biggest lecture. Is there any question